Hi, good morning everybody. My name is Matt Davis. I'm the Managing Director of QA Systems in the UK. I have been with the Cantata technology for a very long time. I got my notification on my HR system that today is my 33rd anniversary of working with the company. So I've been here a long way. So I'm going to talk today about efficient unit and integration testing of safety critical code. Not all of you will be developing safety critical code. There are some lessons that you can learn from the application of safety critical code. What do I mean by safety critical code? Those types of industries. So I'm also going to touch on how our Cantata solution differs and goes beyond the basic xUnit framework set of tools. So my first question, audience participation time, who has used a unit testing tool before? Who's used an xUnit framework testing tool before? Okay, so some have, some haven't. Okay, good. So a couple of definitions just to start out. This is the terrible Wikipedia definition of unit testing, a piece of individual source code fit for use. What it actually means in terms of testing is verifying that unit as an executable, i.e. dynamically running it. So this is different from the static analysis, looking at code statically, but exercising that code in a dynamic environment, whether that's host or target. Principal purpose of unit testing is the correct internal processing and the correct uses of interfaces of that unit to other things. By contrast, the integration testing definition in Wikipedia, what we're looking at really here is a cluster, again verified as an executable, but principally not looking at the internals of each unit, but looking at the interaction between them. So cluster verified as an executable, inter-unit memory allocation, order of calls, data manipulation, etc. Something is trying to call me, so apologies for the background noise. Okay, unit isolation testing. What you might do, very, very simplistic style system. Lots of units, global data. Where might I start? How might I approach this? Well, one technique is top-down. So you take your parents' unit A, and you use that and test the subunits simulated and then calling them as subunits. Different approach, bottom up. The test script drives the child units, and then these units are used as validated or verified inputs to unit E in higher level tests. The third option is test them all as one. So test them as a big integration object. Don't individualize, don't isolation individual units, but test all of the interactions of the units as they go. This is very annoying, isn't it? Fingers crossed somebody will stop calling me. Integration testing, what does that mean? It means taking the units as a cluster and testing them with a script driving at some point. What does that mean? As an integration script, it means multiple units built as a single executable, not individual units as individual executables, with the test script acting as a driver. You may have other libraries or other code involved, so third-party libraries, it might be a boost, it might be an STL, for example, and you're building a test executable. In this circumstance, you are looking at potentially not having all of the code implemented, or where you are implementing the code, wanting to test the interactions. So you have a choice between simulating items that are not complete or intercepting and using items that are complete with a choice of driver entry. So you can choose where in your stack of code you're actually going to start invocation. There's usually no scalability limit for integration testing. There is, however, one big limit, and that's up here, the complexity of what's going on. So this system is not very big. Yeah? If I've got 10,000 units, that's bigger than comprehension very easy in a test. So scalability becomes a matter of understanding what is supposed to go on. And normally with forms of integration testing, and I'm differentiating that from a system test, because you are looking at full unit test capabilities for a script-driven integration test environment. So similarly with Cantata, it doesn't matter if your unit is a single source file with 10 functions, a single source file with 1 function, or 100 source files with 10,000 functions. There is no scalability limit. You can do all the things you can at a unit test, at an integration test. It is just the comprehension of what's supposed to be going on. What do I mean by safety critical code? Well, these industries, illustrated by these graphics, map to these various standards. Virtually all of them are derived from the generic standard IEC 61508, which is often used for general industrial electronics and automation, probably the most one suitable for the guys in the room. But everything from cars through to nuclear power category A control systems, where you really don't want things to go wrong. What it means by safety critical is if the code goes wrong, it either hurts people or kills people. Okay? So, if we're looking at testing in the software development lifecycle, what does that mean? First thing it means is you've got some code, but you don't just magically have code. Yes, you define your code from something as a set of requirements. Now, what level of decomposition you do at each stage, adding more detail from your software to your system requirement, to your software requirements, down to individual items and components, potentially even individual units. You will also find there is a degree of decomposition directly into code. Why? Because people don't write down in requirement specs every single thing that a piece of code should do. Defensive programming, system setup, initialization, these are very common degrees of additional decomposition. The verification order on the right-hand side of the V starts with nothing to do with any of these requirements. It starts with static analysis. The first type of static analysis you might want to do is, does it meet a quality standard? Now, what is your quality standard? It might be as simple as MISRA coding standard. It might be more complex. I want a number of security approaches to apply. I want to look for bugs in advance of spending my time using a testing tool to dynamically verify behavior. Why? Because it's faster. Static analysis tools are great. You run them on the code, they tell you what could be wrong, you can go and fix that before spending any time writing any tests to try and prove it goes wrong. So that's the thing you do first. The first type of testing is, does the code do what it should? What does that mean? It means functional requirements-based testing and non-functional requirements-based testing. And that can occur at any of these levels, right from down at a unit, right through to a system level. Some of them will be different, depending on the nature. So non-functional requirements testing is quite often done at a higher level. These are things like, does it perform at speed? Does it perform with a suitable user interface? Is the user experience good? It might be various other non-functional requirements. But beyond that is, does it not do what it should not do? Does it not go wrong? Yeah. Static analysis will tell you some of those possibilities, but there are lots of others as well. Does it not do what it should not do? That's a form of robustness testing. Please do not test your code with a hammer. That's just an indication to show the idea. The whole concept here is, how hard can I push? In all of the software safety standards, they will dictate that you do some type of robustness testing. This is the one area of testing which is potentially infinite. Don't do infinite testing, you'll never release your code base. You might want to do full requirements-based testing. Does it do everything it should do? Yeah, functionally and non-functionally. But can it not do everything it should not do? May require the infinite possibilities of variations and variables and the amount of computing power that becomes uneconomic to do. So you make a judgment call about what level of robustness testing to do. One element that helps you indicate how much of that should be done is structural code coverage. It is a very common technique mandated by all of the safety critical standards that says, almost as a backstop, after you've done, does it do what it should? Does it not do what it should not, to a reasonable degree? Have I tested all the code? Have I got code here that I haven't got a requirement for? Why is it there? Has it been copied and pasted from some other branch? Is it doing something it should not do and I haven't verified that it shouldn't do it? So structural code coverage for all of the safety standards is a backstop that says, have I tested enough? In other words, is all the code tested with either a functional or a robustness test, and should it be there? The different testing methods, colored by different colors, as you saw on the previous diagram, are listed according to the different standards here. They vary a tiny bit by what's called SIL, or Safety Integrity Level. Each one of these safety standards has various levels. Is it really going to kill people? Does it matter so much? Is it just the color of the indicator on the steering column, or is it something that's going to control the engine control unit in a vehicle and stop it crashing? There are differences, yeah? But nonetheless, these basic techniques across all of these different standards are listed here. As you can see, lots of different types of robustness testing, like error guessing, fault injection, and so on. So, turning to xUnit tools, what are they? Well, they come from Smalltalk's xUnit design, long time ago, 1998, after I started selling Cantata, which is a more commonly known as the JUnit framework, because JUnit followed xUnit. So, xUnit framework shares some basic concepts: a runner, some cases, test fixtures, the big core bit of it, which is assertions, assert that this is that, a test execution, and test results formatter, taking the input and providing some form of result. The frameworks are almost always available as a portable library. So it's not a full testing tool, it's a library that you can pull in from a script or a suite, whatever terminology you want to use. And very importantly, they're open source. They come with open source licensing. That means they are free to acquire. This is not quite the same as free to use, because there's cost associated with using something limited. It also comes with community level support, so you don't have a commercial vendor behind the application. I'm going to contrast a little between the two. Cantata as a commercial level tool for unit and integration testing, fully certified to all of the different safety standards, right up to the highest safety integrity level. And why? Because of test efficiency. I'll come on to the certification right at the end. And that efficiency is driven by automation. An xUnit framework providing you a library is basically a cookbook. I can go and write some code to test some code using a library with a number of basic assertion functions. So, what are these efficiencies beyond the xUnit tool limitations? The first, and by far the most important, is manual test creation. If you are typing your code, and you are typing all of your tests in a code-based framework like an xUnit tool, you're doing a lot of typing. Yes, you have code completion, yes, you have library functions, but nonetheless you are still writing an awful lot of code. By contrast, Cantata as a commercial tool can offer a capability which automatically generates tests for you. As Henrik said right at the beginning of the day, one of the most expensive things in developing embedded software is writing unit tests. If you can have a tool that automates the production of those, it becomes much more efficient. The second one is a stylistic thing. I think this is driven partly by the TDD community, it's partly driven by the nature of the xUnit framework tools. They tend to be black box. So you are taking a function and you're calling it through its public interface, and whatever static functions or private methods are associated with that public API are blind to the test tool. You call through the public API. Why is that limiting? Why is that a less efficient way? Because controlling all of the behavior in that stuff that is static, private, protected is easier with white box testing, where you can intrusively poke the software at that level. Why might you want to do that? Simply, good example, I've got some condition, when this is the 25th time that this function is called, what do? It does something different. Well, I can go in immediately and set it the 24th, call it one time, that's faster. It's white box testing, it's just more efficient. I'll come on to details. Mock simulations. Does anybody here not know what a mock, a dummy, a stub, a fake, or anything like that is? Good, so we're on the right page. There are some limitations to the way simulations work when you are doing unit and integration testing. I will touch on a very powerful, unique capability in Cantata called wrapping, which provides the ability to intercept, not just to simulate. And then there's limited error injection, where you have a basic black box framework and you are driving your software through that with an xUnit tool, you get limited error injection. And I'll touch on a capability we have in Cantata called custom code injection, which goes beyond even what you can do with wrapping to directly inject errors anywhere in the code in a controlled way. And finally, there's lack of tool certification. I mentioned xUnit frameworks are open source. They're not certified. I'll come on to that right at the end. Cantata is fully certified to all the highest levels of tools. And we have just launched a new product called Cantata Hybrid, which I think you've got some information in your pack about. Has anybody here used Google Test? Quite a few, okay. It's a very, very popular xUnit framework tool. It has one major limitation. It's not certified for safety critical use. Okay, so I touched on automatic test case generation. Why do we use it? Because it's hard work not to. It's as simple as that. Even with powerful authoring tools, Cantata has lots of capabilities to help you design and create test cases very efficiently from a test framework saying, I want it to do this. And it will go off and create that. It will understand the code. It will use all of the hooks. It will say, which functions do you want to test? How do you want to test them? Blah, blah, blah. But even with that, which is more than is available in an xUnit framework tool, it takes a lot of effort to write all of this stuff because you're typing a lot of code tests. More importantly and more challengingly is insufficiently validated requirements to test against. Does the code do what it should do? Do I know what it should do? Did anybody write it down? Did they put it in a comment which they didn't update when they changed the code? There are lots of challenges here with insufficiently validated requirements. Are they correctly decomposed, correct, complete, unambiguous, logically consistent? All of those things. I mentioned design decomposition. Even when you have a really detailed spec of what the function should do, some engineer's going to go and type in some defensive program. Ooh, what happens if I run out of memory? What happens if this happens? High reliance on structural code coverage and reverse engineering becomes the result. So you have a load of tests, you've got some code, I've tested everything it's supposed to do, and I haven't tested all the code. So what do? I look at which bit of code is not tested, and I write a test for that bit of code. That's reverse engineering. You are basically testing the code does what the code does because the code is there, and you write a test just to achieve the structural code coverage. It's not a good technique, but a lot of people do it. It's a challenge. The complexity of test vectors. Okay, it's great when your code is simple. If it's greater than 10, do this. If it's less than 10, do that. If you've got a combinatorial effect of lots of different parameters or data affecting the outcome or behavior of your functions, you are looking at things like setting up the preconditions, the inputs, the expected outputs, the order of calls you wish, and the postconditions. Sometimes it is difficult to create the edge conditions for white box testing with hard-to-reach parts of code. I'm not sure which combination of values will give me the output I want. Efficient test case selection. Am I using boundary value analysis? Am I using equivalence classes? Does everybody understand what an equivalence class is? It's basically the same thing as an expected behavior from a variable holding multiple values. So if it can be greater than 10, it could be 10, it could be 11, 12, 13, right up to max int, whatever. Those are all the same equivalence class because they're greater than 10. But they're not 10, and they're not less than 10. So those are 3 equivalence classes of positive integers. So, weigh up the benefits of potentially automatic test case generation. I'm not going to touch, because we haven't got time today, on the alternative, which is generating test cases from requirements. I can tell you we're doing an awful lot of research at the moment in the AI sphere on large language models, on reading requirements and generating test cases automatically. That's not an uncommon thing for a test tool vendor. Watch this space for the roadmap. However, we can generate test cases from code. Why? Because you have code. You have to have code to be able to do the dynamic tests. Your code should be an implementation of your requirements. Somebody's gone and said, it should do this, I will write some code to do this. If you've got code that is meeting your requirements, you can use test vector generation using path solving algorithms and intelligent optimization to create tests for each one of those requirements outputs. If you've got a full test framework, which Cantata is, it allows you to define all the preconditions, inputs, expected behavior through the function, and expected outputs and postconditions. Tests can be generated so they're maintainable and readable in a structured format. They are in Cantata in standard C or C++. And we do this with our functionality called auto test. So we read the code and we generate test cases from the code. Where's the brain come in? There's always a brain. Okay? You can't do everything automatically. The brain comes in. Does the generated test verify the requirement? Why is that a good loop? Why is the closing of that loop important? Because if you've got code that is not implementing the requirement, the test will create a passing test for that code. And if the test says it does X when it's greater than 10, and actually the requirement says it should do Y when it's greater than 10, the code is wrong. So the auto-generation of the test and that linking, that brain thinking, has elicited the failure. How do we do it? We generate a script. You read lots of Cantata options, what coverage you want, whether it's call interface control, interceptions, simulations, black box, white box, OO-style testing, algorithmic-based auto-testing, etc. With those options, we read your code. We parse it. Parsing is an essential element of a powerful testing tool. It basically tells us what's in your code. It's a bit like the models that we were referring to with static analysis earlier. We do a Cantata static information file for every source file under test. You can select them on a command line or the GUI. When you're running with your auto-test algorithm, that pulls in those things and generates 3 different outcomes. Makefiles to build your tests, test scripts containing the test cases, and an auto-generation report, which tells you what you should get. This is it in more detail for the test vector generation process. Start with the source code parse. We use a node graph representation of that. We correlate that with in a test case generator, setting and pulling in the options. So if you want to achieve all the decision outcomes in your code, you ask it to achieve all the decision outcomes. If you want it to do modified condition decision coverage, the highest safety critical level, you ask it to do that, and it will often do it. It uses a combination of an AST, abstract syntax tree, alongside the node graph, and then it uses a combination of a SMT path solver, Gaussian elimination, and generates a number of potential test cases through the code. What does that mean? It's got the path tree. In this case, very simply, 3 different paths through the code, different branches. Are they sufficient? Yes. In which case, it goes off and uses an optimizer inbuilt. I'm not going to generate tons of test cases. I'm not going to bash the code. I'm doing a pinpoint path through the code with each different test vector. So each one's a delta. I then end up with my 3 test cases, and they go into a driver script, and the script and makefiles and the auto-generation report. So considering the paradigm where we are, we've got embedded software, got some software under test up there on the top left. It might call other functions, might call operating system functions, might interact with the target. These are all things that are in scope. So the defined inputs for those are everything to do with the function parameters, the accessible data, the preconditions, the system initialization, etc. The expected behavior is what calls are made by functions, what data is written to and read from, what interrupts are handled from the code as it runs, and expected outputs are things like function returns, accessible data changes, and of course, the code coverage achieved by those tests. So the driver sets that stuff, calls the software under test, defines the inputs and the expected behaviors and expected outputs. The whole point about dynamic testing is, does it do what it should do, what you expect it to do? So you define what you expect and you check and compare that to the actual behavior. So the control of interfaces, everything from simulation and interception, checking the call order. And that might be that one function is intercepted inside the same source file, so it's within the compilation unit boundary of the software under test. It might be going outside to third-party software, which you don't have access to, but you are going to intercept it and check what it does. Same with an OS or compiler library, for example. You might want to simulate or intercept with the physical hardware, so firmware messages or hardware interrupts. An automatic generation creates all the simulated calls, all the interceptions, and calls with wrappers or stubs. Here's an example. We took this is actually from telecom code, originally from Orange, if I remember right. Simple C source code, 541 source files, 807 functions, basically the big numbers. 55,000 lines of executable code. We used our own tool to measure the McCabe cyclomatic complexity, which gives you a really good approximation of the number of decision outcomes in that code. 4,900. It took 2 hours to generate the tests, 36 minutes to execute them. It's now a lot faster than this. We did this a few years ago. Very high levels of code coverage, but more importantly, 4,900 outcomes, 5,035 test cases. Very close to optimal set of test cases for that entire code base. And the depth, 55,000 lines of code, nearly 6 checks per line of code. What are we checking? Everything. The state of data, the state of calls, what's parameters passed backwards, returned backwards, and so on. You don't have to go to that level of detail, but that shows you if you do, it is doable. Okay, use cases in safety critical code. First one is you get a report on generation. Is your source code actually testable? Are there things that are dynamically unreachable? Is there data uninitialized or functions that are static or data that's initialized in functions that are static? Does it create a crash scenario? We don't want a test that's just going to crash. The whole point is that this is not a robustness test. It's a test to prove that the code does what it should do with path solving. So those are some limitations that it will fire up. Test cases can be assigned as requirements-based tests. I'm going to come on to this in a little bit more detail, but you can generate tests and they can be reviewed and used, unaltered or modified, to meet requirements-based verification objectives. Some standards, nobody working in avionics here? Good, you're fortunate. Some standards like DO178C, the avionics standard, says every single test case, no matter how or why it is used, has to be traced as a requirement-based test. You must define a requirement for every single test case. Targeted test case generation. You may already have a load of tests from your system test. You're just trying to plug some gaps in the testing with your unit test. You may already have some unit tests and you want to plug the gaps that you don't know how to get the different combinations of data for. Targeted test case generation is particularly powerful when it comes to complicated metrics like decision coverage and MCDC coverage to help with all those different combinations of boundary values. A couple of little diagrams just to show this is the avionics standard, all require verification of low-level or mid-level integration requirements. So you can see here complies with unit design and fulfills the architecture in the software. This is for automotive, 62304 in the medical space, same sort of thing. Demonstrates traceability between requirements and different levels of tests. So, how do we do the efficient tracing and why? Well, the first thing is why is because if I'm generating tests from code and I need to say, is that test a valid verification of the requirement, I need to know what the requirements are. I need to be able to link them. Yeah? If I'm going to have all the tests, the tests are proving that all of the code is tested to show that it does what it should, I need to know what the list is of what it should. Okay? So, how do we do it in Cantata? We import it. By the way, there's nothing for this in xUnit tools. All right? They just don't have the framework for it. Bidirectional requirements traceability. We import requirements from a requirements management tool or ALM tool. Yep, that could be a powerful one like Doors or Codebeamer or Integrity or Polarian, etc. Or it could be like what most people use, Excel, because it's on your desktop and it's cheap. Yep, and you can do pivot tables. So we can import the requirements in 3 formats: CSV, Excel, or something called RecIF, the requirements interchange format, which is an XML, specialized XML for requirements tools. Gives you lots of extra data. Cantata, you have a drag and drop interface, so you can see the requirements inside the Cantata tool, compare them to the test that's verifying that requirement, and say, yep, link. What does that look like? Looks like this. This one's very flat because it's Excel, so I've got a system set of requirements. For example, when system valid returns OK, check status, global data int shall be set to OK. Yep. Set of requirements, set of tests. Take a test, drag it across to the requirement, and it's added and assigned. This one is an auto-test generated test. So this test case on the left is created to solve the true case of average B greater than 18.25 at line number 35. Autotest helps you do this by giving you that level of detail. Why was this test vector different from any other? The explanation and the location. And because of that explanation and location, I can very easily map that to the requirement. This works well when your low-level requirements are nice and detailed. The less detailed your requirements, the harder requirements traceability is. This function should do the right thing. It is not a good requirement. Yep, you can write some tests for it, and you can link them all to that requirement, but it's not easy to make the correct calculation. So drag and drop, auto test, path solving description aid the linking, whether it's a test case or a test script. And a controlled export contains all of that link, passes it back to the requirements management tool or Excel, so another tab in Excel, for example, or updated tab with all of the data and the code coverage achieved and the status of the test. That gives you in the one thing that you control, your full bidirectional traceability. The reason we don't do it inside Cantata and keep it in Cantata is what do you trace your requirements to? Tests, but everything else. Yeah? Review records, contracts, source code items, third-party libraries, the whole lot. So you keep it in your repository. We help you by providing a link. It aids. Traceability helps you identify gaps in requirements-based tests. I've now got some code. I've got a test for it because my auto test generated a test. It doesn't link to any requirements. I've got some code doing something. I haven't a clue why it's there. Yep, I either decide to write a requirement for it or get rid of the piece of code. I can identify gaps, overlaps, and duplications. It gives me the visibility with a traceability matrix, and it supports requirements coverage as well as code coverage and test coverage. Unfortunately, never things stay the same, so your requirements change. Who in this room has had a set of requirements for an application that has never changed?
What is a requirement?
A requirement is, a requirement could be anything. Honestly, it could be a JIRA bug report, fix this. Yeah, but everybody has changing requirements. So, of course, my issue here is requirements change, they're going to impact your tests if they're requirements-based tests. So Cantata also, in its Cantata trace capability, allows you to identify new, changed, and deleted requirements. As you can see here, there's special filters that allow you to say this set of requirements varies by what. The more data you have in the information you pass into Cantata, the more information it can present to you. So you can focus on what has changed for testing. You can handle versions and variants of requirements for traceability. Unfortunately, it's not just requirements that change, it's also your code that changes. So when it comes to test maintenance, Cantata has an impact analysis and change-based testing approach to the way in which it looks at this. For easier test maintenance, it basically stores the last state of the software under test, compares it to the current state, and you can run and identify the impacted tests and changes. And what? Well, all of those different things. So if a function or a method, for example, has been added or removed, the signature, either its scope, return type, name, or individual parameters, any of that has changed, it'll be an impacted test. So it identifies specific changes for you. This has changed. My variable new static data has been added to the file. What do I want to do with it? They're all hyperlinked to a code editor, and it gives you suggested options. So do I want to add that piece of variable to my test? Yep. Okay, moving on to another capability area that is different from xUnit. I talked about black box and white box. With black box tests, you might want to do every single test as a standalone test, or you might want to do it parameterized. Google Test, for example, has lots of looping parameterized tests, a sort of table-driven approach. We have the same inside Cantata, particularly good for robustness testing. You're going to bash lots of values at it rather than just one. It's a more efficient way of doing it. But also you might want to put tests inside encapsulated code, so private or static data, for example. The little graphic basically gives you the description, black box, white box, sometimes known as clear box, because you're going inside and controlling the internals. So where Cantata is providing power and precision on table-driven tests using multiple values for parameters or data inputs, user can define selected or predefined looping tests and import and export that data via CSV. All available in the interface. Automated accessibility instrumentation means it will call private methods and static functions directly to be able to set and check data, particularly good for trigger values. Put it in the state precondition, give it an injection, do it something, see what happens. Is it the right thing? You can also use interception and simulation of calls within the compiled object. That means interception. I will come on to that next. If you've got an isolation unit test on the left-hand side, you've got script, you've got function, it might call things. You might want to do different stuff with it. Very commonly, I've got my mouse. Is it working? It's not coming on screen. Function B over there on the left-hand side, I'll use my finger. That's a standard simulation. That's where your dummy, your mock, your fake, your simulation comes in. If you're within your compilation boundary, so you're compiling functions A, B, C, D all together in the same unit, it's much harder to simulate mock an object that is already in the compilation boundary because you have duplicate references. For an integration test, that problem just explodes. Okay? The more you put inside your compilation unit boundary, the more you are dealing with the thing that is integrated. And why would you simulate something you want to actually use to test it does the real thing? So automatic generation in Cantata gives you the stub simulation and the wrapper interceptions, depending on the type of call that's being made and where the call is within the compilation unit boundary or outside it. But not only that, inside each one are programmable instances, so you can do different things on different occasions. And efficiently, you can reuse those across multiple tests. So you can have certain tests that say, do this and just behave as normal. I know I'm calling malloc, yeah, and I just want it to run as normal. But in one test case, I want not to use malloc. In normal, I want to inject an error. I've run out of memory, and therefore I'm going to trigger something to be the return. You can have very flexible call sequences. You can have one per test case. You can have multiple interleaved parallel call sequences. It's very complex and powerful. This is a nice, simple way of just showing it. When I simulate, I have a stub, and it replaces the object at link time. Isolate is a specialized form of wrapper, and it replaces specific calls at runtime. I don't use it. I simulate it, but I can check, and I can push things back. Yep. This is my mock object. If I'm going to intercept calls, I can have a before-after or a before-replace pairing, and I'm intercepting those calls at runtime. Cantata creates wrappers. You can do exactly the same as you can with a mock simulation. Check things on the way out. But you can also modify things to this real thing. Now, it might not be change anything into it. It might not be changing a parameter. It might be changing another precondition, such as a piece of global data. You might want to flip a hardware register at this point, see what happens with this code. But this is the most powerful one. You can check. If you're doing a simulation, you are basically testing your source code when you say this called object does X. And you are assuming the source code, this thing over here, does X. If it's not your code, it might not do X. So you can actually check it at this point, as well as set and check other post conditions, and modify returns and parameters back to the source code. This is the standard before after. It's created by default, and it doesn't force you to check anything if you don't want to, but it provides you a hook to be able to. But it also allows you to do the replace on any individual call from function in your source code to something else. That called object can be anything, third-party library, database, Java code, something else. You can simulate it. So you can choose, use it or simulate it on any single call. Main advantages for this integration testing, you can check rather than guess. Test scenarios based on a simulation that is false are not a good test scenario. Yeah? I assume it will do X, but it doesn't actually do X, it does something else. I retain all the control of isolation testing when I get to integration testing. So you can set up test preconditions faster with white box access, and you can inject errors at this call boundary. So when the call happens, you have control again. Normally with a test framework, you call the function, it goes off and does its thing, and you check that it did its thing. Here, when a call happens, you get control again as the tester. So every function call gives you that opportunity to control. That's versatile. You can scale it up to integrated software, and it can test with hardware in the loop, software in the loop. You can simulate hardware failures very easily with wrapping. It's a particularly powerful scenario for it. But beyond that, we can do custom code injections because you only have control at the call boundary with wrapping. You might want more fine-grained test control. Cantata custom code injection allows you to put it on any statement, anywhere in the code. Before or after any statement, more flexible than wrapping at the call boundary. You don't have to use conditional compilation and pollute your production code stream, and you don't have to use a debugger, which is non-repeatable. Types of use cases: inject an error anywhere, change a local variable, fire an interrupt, break out of an infinite loop, which is always a problem for testing. And you can even use it to trial code changes. If you're the tester and you're not the coder, you can say, ha, found a bug, this is the fix, see the fix, it works with the fix, there's the fix file. Go add that to your code. They're controlled by instrumentation. So you do it or you don't do it on any particular build of the test. Injection is stored as a snippet file, very easy to read, and it's used with each custom code injection in the test properties for each script. So, when it comes to test execution, one of the things that sometimes happens is that people test unit tests on host because it's cheaper and easier and faster, and you don't have the physical hardware in the loop, and sometimes you do need to test on the hardware, so you do both. And platform differences can be verified by running tests on both. The way that Cantata is structured, unlike an xUnit framework tool, because basically you build the test for the environment, so you have a whole duplicate of your tests for your host and a duplicate of your test for your target. Cantata has platform-independent tests, pulls in the software under test, takes a copy of the source code, so your production code is never modified by any of this clever white box instrumentation or code coverage. It has a platform-specific, so for example, for a host test framework, pull the options, you build your test, you run it, bang, you get your results. How you run it could be anything. You could run it on the command line. You can run it under all millions of IDEs. You can run it Eclipse, VS Code, everything the way that people and I like to do. But if you're going to do it cross-compilation, you get to choose. You have different configurations of Cantata set up for using different cross-compilers and different target environments. So you can have a target test framework that builds a different executable, the cross-compilation one, which is then flashed to the board. Connections of various types. When it's run on the target, you get output. Now, not everybody has super file I/O on a big fat RTOS. Most people don't. I'd say about 90% of our customer base don't. So we use an automatic multiplexer and demultiplexer to take character streams or flash memory buffers or whatever from target to host. Sticking it into a CI/CD, Cantata makefile system works with existing makefile systems, can be used with an existing code tree if you don't want to use sandboxing. It's basically a hierarchy of gmake files with separate target builds. It also runs with CMake and various other combinations. And it allows you full build for regression testing. Because if you are going to do unit testing, don't just do it once. Keep doing it. That's the whole point. You'll lose all of the value if you don't. One of the most powerful things in Cantata hierarchy of makefiles is custom.mk. It's a customizable pre and post build command, so it allows you to do anything. You can trigger your static analysis run with Code Sonar at exactly the same time you run a build with Cantata. Yeah, you can plug something into an SCM tool. You can fire the result after the test. If it's a failure, fire up Jira and log a bug track. Yeah, you can stick it in your dashboarding. Touched on pipelines briefly this morning, so just an indication, you run your static analysis before you do your dynamic unit test on host or targets. Again, we Dockerize, it's very simple to do. It's really sensible. Some people use virtual machines, VMs from VMware or whatever, but most people don't. Being able to run it on various host and targets for unit and integration testing, and then you end up with no more manual installations. Deploying the tooling as code, infrastructure as code, if you like that terminology. Automated DevSecOps testing. And one of the things that some of my weird techie colleagues like to refer to, null release minimization. When I change one small thing, what is the minimum set of stuff I have to do? So with our impact analysis, change-based testing, it reduces the minimization, and it's quick. If you do it with a narrow set of focused changes, whether it's requirements changes, code changes, or even test framework changes, minimizing that and doing it at speed means the checking works faster, and people are happy to do it continuously. If you're sitting there waiting for an hour for your test to run, and you're going to do it that day, you're going to leave it till overnight, how continuous does it become? Efficient reporting. So there is an add-on to Cantata. There's an extra tool if you want it. That gives management data. Yep, we put that all on a server. It's all available on a database with a REST API. There is a web interface for it, but it basically aggregates and basically allows you to slice and dice the data, see it over history of trends and things. You can even differentiate between test runs with different environment variables, so run on this target, or this build variant, this compiler version, optimization, whatever. It even allows teams to collaborate because you don't actually have to replicate the environment. You can see the results with all the details. That's an example Jenkins set, mostly for afterwards. You can see all of the different possibilities in terms of pulling it, pushing it, running a test with or without coverage, or with or without requirements traceability. The reports are linked from Jenkins or Git, so you can get them directly into Cantata team reporting, and this is the type of dashboarding that you can get. Trending, history, results filtering, etc. Last big difference I touched on with xUnit tools. They are open source. They're not certified or qualified for safety critical use. All of the safety standards say you should use tools that are suitable for use. They all have a tool qualification requirement. How well qualified is this tool for the purpose you're using it? There are different qualifications depending on whether it's a runtime component, for example, an RTOS or a library that you're putting into your production code, or whether it's a verification tool, like a static analysis tool or a unit testing tool. Cantata is independently certified by SGS TÜV. Gosh knows how the TÜV market got suddenly so big and all dominated by the Germans. I don't know why, they've just hoovered up everybody, but we chose SGS TÜV. They certify to the highest level of integrity for all the main standards. We provide a tool certification kit, but it is not just a certification kit with a certificate, it's a certification report, a very comprehensive safety manual, currently 82 pages, I know because I just updated it, standard-specific briefings. Again, many tens of pages doing line-by-line mapping of all the requirements of a safety standard to how you can meet that inside Cantata. We don't just say, you can use this, we show you how. For DO178C, the avionics guys, they can't do it with a certificate, so we have to provide them with a tool qualification kit. Our certifiers use the DO178 tool qualification kit materials and all the evidence when they certify our tool. Then you've got the extra problem. xUnit tools don't have certification and qualification. What did we do there? Well, before we said, throw it away. Stick it inside a certified tool. But now we have a different option. Fingers crossed, this works.
Do you need to certify your Google tests? If you are developing safety-critical software to one of these standards, your tools need to be qualified or independently certified as suitable for use. Each standard defines the process required for tool qualification or certification. Google Test, including Google Mock, is not certified as a unit test tool. So what do? Well, you could qualify Google Test for your project, or you could migrate all your Google Test cases to a safety-certified unit test tool. Both options are risky, very time-consuming and expensive. Now there's a better option, Cantata Hybrid, a unique solution that runs your unchanged Google Test through Cantata technology to generate standards-compliant test evidence and code coverage from a certified unit test tool. With Google Test alone, your suite uses the uncertified Google Test library in an executable to drive the code and check its behavior. With Cantata Hybrid, a compiler wrapper sets options, reads the Google Test Suite, and instruments a copy of the code with Cantata directives equivalent to Google Test macros. The build hybrid executable drives the code and checks its behavior with both Google Test macros and Cantata directives. This parallel execution is possible because the Google Test Framework matches the Cantata core technology test harness. When the Cantata Hybrid Test executable completes, both the Google Test results and Cantata results including code coverage are reported. The detailed test and aggregate code coverage reports generated in ASCII and HTML formats are suitable as certification evidence of unit testing for all functional safety standards. Avoid qualifying Google Test yourself, creating requirements and tests for every macro used. Avoid migrating tests, buying a certified tool, and risking incorrect transfer of data. Avoid learning a completely different unit test tool. Cantata Hybrid runs all Google Test Suites on Change, on any host or target platform, and includes code coverage up to MCDC. If your Google tests don't deliver 100% code coverage or meet other test objectives, standard Cantata can be used to plug the gaps. Cantata Hybrid is certified for use across all safety-critical industries. This hybrid of Cantata and Google Test delivers a fully automated certification engine for Google tests.
Thank you. That's my time up. Any questions?